The most recent concept here on our project is the software product line, which is already more than 10 years old, this concept. What's not on the title is that we did this product line with ADA83, so it's, well, I should say, a mature technology. The interesting point is here to implement a more advanced concept with a technology which is a bit outdated and does not really provide the features you normally need to do implement these concepts. The way to solve the problem is to, for us, what we call it, to rely on three pillars. One is architecture, which is the main subject of today. And the other is code generation, similar to what we've heard just about a minute ago, and the use of patterns. Myself, I joined the project in 2002, where I was tasked with developing a concept to handle the system variants and the software variants, and to supervise the implementation of that concept. So it was kind of a project in the project. And Richard was one of the main contributors. He was the lead software architect at that time. And so we want to share this presentation. I will do the more general part, introducing you to the project and to the main concepts of the product line. And Richard will then take over to talk about the architecture in more detail. Okay, let's start about the project. The NH90 is a medium-weight, multi-role military helicopter supposed to be ready by the 90s, which we didn't really meet. It was initially planned for two basic versions. Or let me say, the multi-role is already a sign that there are many variants, which was at the beginning not really considered. So we introduced variants later during the project, or variant handling. The two basic versions are the TTH, Tactical Transport Helicopter, and the NATO Fragment helicopter, the NFH. And as you see, these helicopters sold already in more than 500 helicopters with more than 23 variants. This 23 is referring to contractual variants. There are many more technical variants behind these commercial variants. What you will see here is quite common, is a cockpit mock-up of the NH90, which was probably not actual anymore. You see here in that variant 5 displays, multifunctional displays, and at the center console 2 DKUs, these alphanumeric input devices. And the whole avionics system, who drives this human-machine interface, is divided into two major subsystems. One is called the core management, the core system, which was intended to be stable for all variants, and the mission system, which is adapted to the different missions of the customers. In fact, it's proved that the core system was also subject to many changes on variants. These two subsystems are driven by two main computers. When I talk about main computers, these are the core management computer, CMTC, and the mission tactical computer, MTC. These computers drive the MILBUS architecture of these subsystems. Of course, both subsystems are connected. And there's also this display and keyboard unit, which is normally referred to as CDU, is part of the development responsibilities of Eurocopter Germany. So the software of these two computers and the DKU was developed in Germany. This slide shows our problem. As you see, we started moderate in '95 with these two basic variants. And it slightly increased during 2001, but still, I think, a manageable number of variants, but exploded in 2002. And again in 2006, 6. As you see here, that's the way the customers were added. So there were more customers. It proved to be rather successful, the NH90. And with additional customers, there were additional requirements, additional equipment, additional functional requirements, and additional mission requirements, which had to be catered for. And so with this high number of variants, an ad hoc approach was no longer feasible. You will hear we do not only have functional variants, we also have platform variants. That is part of the, I would say, the duration of the project. So we have several versions of processes and several generations of processes, starting from the 6840 and up to the PowerPC for the last, for the third platform. You see the platform were also attributed to certain customers. And you see also the implementation technology changed. We started with ADA83, and that's the main code base we have is in ADA83. And there were customers demanding ADA95, but there's no later ADA versions in the project. In order to handle these variants, we came across the concept of the software product line. And the idea behind that is that we try to handle all future and all current helicopter variants out of this single product line. The idea is to have what is called asset, which can be reused for all these different variants. And what we had at that time was a problem with integration of the software. So if we want to turn out many variants, you have to have a very efficient integration process, which was not the case at that time. And there will be upgrades, there will be new customers, hopefully, and they will demand new features and functions. And to ease that integration, we also need that to extend that concept to also to features and functions which are not known yet at this time. One of the major constraints is investment protections. As I said, it's a huge code base in ADA83 code, and you can't throw that away. And for certain reasons, we couldn't just move to ADA95. And so we had to reuse that code. We couldn't throw that away. The same applies to the architecture, which gracefully was already feasible or useful for this kind of concept. The basic concept behind the product line concept is the feature. Feature is a contractable or property or function visible on contractual level. So the customer will order features for that. For example, data link capability for his radio is a feature, or a certain radio, or a SATCOM, satellite communication capability. The main idea is to have, when you don't have only software, you have all sorts of documents. In fact, there are more documents than software. And the main problem is to make an efficient product line in that domain is also to generate or integrate the documentation from what we call assets here. So what we try to do is to modularize not only the source code accordingly, but also software requirements, interface requirements, or parts of the model. And that what we try to achieve is to simply take these modules and assemble that during the integration process. So what comes in is a set of helicopter variants. And there's also a specialty here. We do not make software for a single helicopter variant, but usually for a set of helicopter variants. So a single executable runs or may run on different variants. So the executable must detect the actual variant it's running on and then select the functions which are needed for that. So the idea is to select the features which are required for these variants, combine, draw from the asset base all necessary modules, integrate them hopefully in an automatic way, not hopefully, but that's the intention. We do not achieve that 100%. So we always have to do some adjustments manually, but the goal is to make this fully automatic and to generate then software, the whole software and the documentation out of that. To do that, it's necessary for the modules to be self-contained. What we do not want is have to have any variant decision logic within the code, for example. So we banned all if variant is TTH something, then do that. Because that code breaks as soon as you add a new variant to the code base. When you try to do that, you have certain constraints in your way you implement these, what is called a variability, because there are some restrictions in our domain. The first one is we need, what we have talked already about, is strict deterministic and predictable behavior. So adding and removing features should not break the predictability or the schedulability analysis of the software. We have also to consider the DO178B, and one of the requirements there is there's no dead code allowed in your software, so all code must be somewhere exercised. What they allow is deactivated code, which we have, because if you have executable which runs in multiple variants, in certain variants, certain functions will be deactivated. We also see in the literature, the implementation of software product lines is well established, I should say, but many implementation techniques use object orientation. And at least at our times, there was strong concerns against these object-oriented features that probably will now be relieved with the DO178C. I think this is tomorrow a discussion on that. And the last point is here, and also very important for us, is that we try to achieve a true ADA solution, which there's no preprocessors and no if-defs. So what we'd like to do is to completely in the standard ADA. Okay.
Okay, so Frank mentioned that one of the building blocks of our capability to handle this variant management was the basic software architecture. We've got a leveled system. In its very simplest form, we have the at the bottom level, we have the platform software. This is the software that's provided by the manufacturer of the computer that we run our software on. We've defined an API to our low-level operating system, or NH90 system software it's called. This is the NSS, which is a kernel. This software runs on all variants. We have the ability to adapt the NSS. The NSS typically contains all the I/O drivers for the Milbus, for ARINC, RS485, so on and so forth. It also has all the basic scheduling algorithms and so on. And obviously for the different computers, CMC and an MTC, they host different applications. The Milbus frames are different messages, different remote terminals, so on and so forth. So there is a part of the NSS, which we call the NSS adaptation, which is different for the CMC and different for the MTC, and it makes the common part of the software work for that computer. What's important is that we don't allow adaptation into a mixed module. It's in a standalone compilation unit, and over 80% of this adaptation we try and generate, and some very small stuff we do by hand because it's not worth writing a generator and qualifying it. And on the top level we have the actual application software, which makes a CMC a CMC or makes an MTC an MTC. So it's very high level. Now we go on to the actual generic architecture within both computers. We call it a CMTC, which is generically either a CMC or an MTC. It's quite an old-fashioned type of architecture. We have a top-level scheduler, which is, because it's working basically with a Milbus, it's a cyclic scheduler. The arrows show the effectively visibility of the system, so the system controls at the top level, it can see everything. The virtual subsystems, this is effectively a global data object. They represent, abstract the subsystems within the avionics system, so you'll have a navigation virtual subsystem, and there's a data representation of all the data that is needed by these computers. The system drivers, they don't know anything about the operational structure of this data. They're just byte streams and they just move the data in and out of the computer using the provided equipment software, platform software. So the drivers just shovel data into the virtual subsystems, and then the operational functions, which are the application parts, then access this data, but from an operational sense. So here we're using representation clauses for them and access routines, and we convert the data from its ICD format into an engineering format. For acyclic message passing, we use a sporadic consumer task, and these messages go via the system queue. And I'll explain that in a bit more detail later. So that's the basic architecture. The trick is, when you have different variants, basically you have a completely different set of operational functions. And with Ada, with the widths, this is fairly static. We haven't got any dynamic way of adjusting this, so we have to come up with a solution. And I'll talk about that in a minute. Okay, for cyclic processing, the way it works is that we, as Frank mentioned earlier, we have what we call an extract variant set. So we select from the database a set of variants that we want to actually produce a concrete executable for. We have a database with all the definitions in, and we extract the data for that and generate, basically using Ada skeleton templates, Ada code. And in this case, it's a button database. We call all the operational services that are provided by the OPFs buttons, because the system controller doesn't know what's in them. They're just buttons that have to be pressed at a particular frequency. That's just our naming convention. And each of these buttons, it runs at a periodic frequency, 50 hertz, 25 hertz, down to 1 hertz. And this matches the basic frequencies that are on the Milbus and on the ARINC bus. The button database encapsulates not only which variant this button has to run for, but also the system roles and modes. So we have maintenance modes, operational, redundant. The two computers are redundant, so we have a different set of operations running on the passive computer to the active bus controller. And because looking up this information at a cyclic basis is quite inefficient, when we change the system context, we configure, we parse the button database, extract all the functions that are applicable for this variant in this role, in this mode, and we set it into an activation list, one for each cyclic frequency. And then at runtime, we have a corresponding set of periodic Ada tasks, which then go through a dispatch routine. The problem with Ada 83, and explicitly the compiler that we use, you're not allowed to use function pointers or anything like this. So we've had to use an enormous case statement, which we generate from the Odin database, which comes in with an enumeration ID and then dispatches it to the active variant, which is running at runtime. This is encoded in a non-volatile memory section, which we read on startup, and then set one single variable which says I am this variant. And then when it builds up the activation list, it will only dispatch to the services that actually should be run at this point. So we have a single place, and it's much easier to demonstrate to DO178B that you've actually got a single point where this is all controlled from. So that's sort of a manager's diagram. For software engineers, it looks a bit like that. So when we configure, we get the variant. We then loop over all periodic tasks. Where's the... Oh, there we go. So for each periodic task in the periodic button database, we use a simple integer to say all the tasks for 50 Hertz, they start at position 16 in the table and they run through to position 40. And then that goes back to the loop, and then it knows which part of the database it has to pass. And then the actual data in the database is, you see, you've got for variant A this function identified by the enumeration capability A process P1 should be run on the A variant. In all other variants, it shouldn't run. And it's also valid to run in when it's running as the active bus controller in master role, and also in the slave role, and in the operational and maintenance. And it's valid for the P1 task. So the predicate function comes in with the index. It says, index number 16, should it be run? And it comes back with a simple Boolean yes or no. Okay, so during runtime, in the operational running of the system, we have a simple dispatcher, which first of all, before entry at its allocated time, it just gets its activation list and then passes over this list, extracting the enumeration ID of what the button that should run, and then dispatching that routine. So it's quite simple. And underneath you see the generated case statement. It's not very pretty, but it's generated code, and that's not really a big problem. So obviously, if you were using full object orientation, maybe ADA95 with function pointers, so you wouldn't have to do this, but because of the technology that we're constrained to, this is the way we've actually solved the problem. Okay, so in event handling, very similar. I won't really go through it in any detail. The only difference here is, instead of pre-processing which events can be run or which buttons can be run, we do it on the fly as we need it. So every time an event is read out to the queue, we check to see if it's valid for the current helicopter role and mode, and then we dispatch it. In this case, I show that the runtime variant is B, so the capability A is now deactivated code. So the basic mechanism, you have a producer of the event writes to a special data item which enqueues the event into the system queue. Then the sporadic consumer task runs and starts dequeues the events, checks to see if it's permitted. If it's permitted, then it dispatches it to the consumer. This is the basic acyclic message passing process that we use in NH90. And now I'll hand back to Frank, who'll lead you through the
All right.
software development and generation process.
Exactly. So that's part of, if you introduce a product line, you don't only have to cater for the code or the architecture, you usually have to tackle all areas like from process, tools, and organization too. And the next thing here is the process supported by certain tools. So, you might recognize DORS, which is only used to generate documents which were then manually captured by the software designer. So there was no really way through into the rest of the tools. And also the UML tool here is mostly used for documentation purposes. We use class diagrams. We do generate 8 aspects from that, but we do not, as in the previous presentation, first presentation today, generate more code of it. So that's all manually coded. Where we spent a lot of work was to develop these proprietary databases. So these databases contain interface data, which are necessary to drive or to get data from the equipment. There are up to 10,000 signal definitions for a single bus in this one. So it's a huge amount of data. We can't handle this with Excel, so we use an Oracle database for that. Similar here, the HMI definitions on the DK units, as you'd like, so all the pages, the page definitions, the commands, and key presses that are defined in the HMA database, also an Oracle database with the same amount of data. So we have a huge amount of data here. The advantage of Oracle databases is that you can program some sort of consistency checks within that. So these databases were, the data here were entered by systems engineers. We import that into a database which is called Odin, and enhance that data by software engineering data. For example, the mapping between the raw data on the buses and the ADA representation of that data is handled or defined in the Odin database. As Richard said, we generate from that with a set of Perl scripts and templates the source code necessary. And it's a huge amount. I think it was one time 70%. It went a bit down in the recently, but the idea is to have this is the major part of the adaptation which I talked about. So the generated code went also into the QuickCase database here. And the main point is that the selection of the data to be used in the generation process is feature-based and not activity selected because of the amount of data that wouldn't be possible. The third point here is we introduced software patterns. The standard definition for a software pattern is a standard solution for recurring design problems. And we use that for 2 main reasons. The team at its prime time were about 70 software engineers. And you know that not every engineer is as productive as the other one. If they have a short time in the project, they can't really understand all the intricacies of the software architecture. So we need to provide some help to them. One point is architectures are susceptible to decay, which is very critical in a normal project, but devastating in a software product line process, because if your architecture decays, you won't achieve the reusability you intend. The other point is sometimes the developer had to do some tricky solutions to get real modularized, to modularize it correctly, to avoid any variant dependencies within the modules. And to help them doing that, we developed some standard solutions to the problems they encounter. What we did is we used the naming or the intention and the way it's described from the literature, namely what's called the Gang of Four. But the actual implementation is, of course, not the way it's done in that book, because have because of the lack of object orientation. So instead, our implementation description said how we can implement these patterns with the architectural features we have. For instance, there's certain event handling, certain way to generate things. So in fact, we did replace these features, inheritance and polymorphism, by our features, our architecture features and tool features. Due to shortage of time, we can't explain that in detail. We have listed here some patterns. Only the second is really, you will find in the Gang of Four literature. The other one is an important aspect, configure a component. As I said, we like to have components which are completely self-contained. You can't achieve that anywhere in all cases because sometimes it's inefficient. For example, we have a requirement of different length of waypoint lists. So the waypoint lists we manage have different sizes. Making that a component is not feasible. So we have to adjust components just by certain data. And the way to do it is described in that configurable component. The mapping registry, I think you mentioned it shortly, is it's type mapping in 883, which must be flexible or variant dependent, and also central. So that's we devised here a way to handle that with 883. And all that was the pattern description were placed into a project wiki, so they were easily maintainable and at the hands of every software engineer in the team. To sum up, what we tried here is an example of a product line in a complex environment, complex project, which is also constrained by certain regulations, which we heard about this morning. And these are our three pillars I mentioned. So it's architecture, generation, and patterns, where we talk mostly about architecture. The constraints we have is well, I said, the domain regulations, most DO178B, or some military standards like the 2167. And we have to face the problem of that we have an outdated technology, virtually. And what we also had to do, we had to leverage the existing design and code base, just for purpose of investment protection. We were able to achieve a significant reduction in effort for updates of existing variants from weeks to days, yes, a couple of days, and creating new variants out of the asset base instead of cloning them. A week or a couple of weeks instead of months. Previously it was months when we do the clone and own approach. A side effect actually was that when we went through the code and tried to modularize it properly, we find a lot of problems with duplicated code, for example. So we removed that and could increase also the quality and transparency and the maintainability at all of the software. So that was a positive side effect of introducing an advanced concept into the project. Yeah, I think that's it. And we are now open to questions.